we'll be talking about deep learning. A few announcements. Mini Project 2 has been released. The project is poem generation using HMM. So the training set is all the Shakespearean sonnets. Have fun. You can work in groups of up to 3, so recommended in 2 or 3, and it's due on March 10th by noon.
How do you evaluate the results?
We'll have the standard, well, we'll look at your implementation. So you have to implement a couple of things in HMM as a group. We'll make you visualize parts of the HMM model, like what did this hidden state in the probability table, what distribution of words does it correspond to? And at the very end, you will submit one sentence generated by your model for a competition to be judged by the TAs. One sentence, one poem, excuse me. One poem generated by your model. So it should be fun. And yeah, it's due March 10th. That'll be the last thing that's due before the final. The final is a take-home exam. It'll be released on March 14th, and I haven't decided exact window yet, but something like 24 to 36 hours. It is intended to take 3 hours to do, so significantly shorter than homeworks. You're given flexibility to take it any time you want in this window, so please don't think that you have to take 24 hours on this final. That is not the intention. And open book on everything on the course website and any Wikipedia entries. But on this for the final, no collaboration. You can't discuss, with anyone. You could, for clarification questions, you could of course ask on Piazza. Okay. Okay. So today, before we talk about deep learning, let's first talk about linear models, since that sort of the contrast will highlight what are some of the limitations of linear models. So in a linear model, something that we've become very accustomed to in this class. You have a scoring function that's linear that's W, that's linear in the feature representation of the raw feature representation X, and maybe there's a bias term, right? Sometimes we have a single nonlinear transform that transforms this linear scoring function using some transfer function, such as this tau. It's typically a monotonic transfer function, so always increasing. So much of deep learning, the popularity of deep learning these days, is built on the back of multi-class classification, such as given an image, classify whether or not there's a car in this image or some other object, right? That's an instance of multi-class classification. So binary logistic regression looks like this, where there's y is one of 2 classes, and then it has a linear property, you extend to multi-class. In this way, where now y can take on one of k values of k's number of classes. In practice, k can be quite large. K can be 1,000, for example, if you were trying to recognize whether or not an image contains one of 1,000 objects. And it's typically, takes this form. Right? And so you have a feature representation X that you like, and you can learn a model to score the affinity of this feature representation to each of the classes, and then you have this sort of probability distribution based on the exponentiation of that affinity. Okay, so this should all be reviewed at this point, trained by a gradient. So keep this in mind, because we'll actually be using this later on in this lecture, just that we won't be sticking with linear models. So here's an example that I think is quite challenging for a linear model, right? So given a image of a handwritten digit, like 2 or 9, predict what digit this is. So this is a 10-class classification problem between 0 to 9. And we wanted to learn, and you can think of X as simply if you vectorize this array of images, it's black and white in this particular case. If you vectorize it, it's simply just a vector of black and white, 0, 1. I guess is there shades of gray? Or there might be shades of gray, but let's say 0, 1 feature values. And let's say for simplicity that all the images inputted to this model is of the same size. So it's going to be scaled to be, let's say, 128 by 128, whatever, right? Okay, so the question here is, okay, suppose we want to build a model that looks like this, where this is the input. What should be the feature representation, right? Naively, using the type of linear models that we've seen in class, we would just say, well, we just use the native feature representation, right? Because that's what we're given. So in that case, each pixel is a feature, right? So if we do that on this data set, which is the MNIST data set, logistic regression on the training set yields about 80% accuracy on the test set. Okay, so okay, that's not too bad, but it's not usable in practice. And these days, for example, many delivery services, they do automatic address recognition from people even scribble their address on some, like an envelope that you mail. So 80% is not good enough for that. Okay, so what are some errors that a linear model might make on this type of data set? Well, it can often make a mistake on 8s. So for example, it can predict that this input has a higher probability of being a 3 or a 5 than an 8, right? And you can sort of see why that is the case, right? An 8 certainly shares a lot of sort of pixels with 5s and 3s, right? And it's, in a sense, at a high level, the reason why it makes mistakes like this is because a linear model on the raw pixel values is not powerful enough because it doesn't capture interactions between pixels, right? It just says sum up the pixel intensities and figure out if my linear model cares about the pixel here being white or not, sum that all up, and that's my score, right? It doesn't measure at all sort of interactions between pixels. Like, if there is a curve here, that matters a lot more than if there isn't. And the curve needs to be a complete curve, not just a partial curve, right? So those are properties that are not captured by linear models. Okay, so the punchline basically is that linear models require good feature engineering in order to be effective, right? So here's some features that one could create. So these are edge detection features with a little bit of blurring, so you subsample. So you can think of these as oriented gradients. So if this is your raw image, then you create these set of features which activate when there is an edge. There's an edge from light to dark, or an edge from dark to light, top down, or left right, right? So these are features. So you could think about creating a feature vector that looks like this, and these are basically called oriented gradients, right? Top edge, left edge, top edge. Okay, so if you use these as features, logistic regression gets you 90% accuracy, which is significantly better than 80%, and gets you closer to the regime where you could actually use this in an actual service, deployable service, right? And so one reason why this type of representation gives you more representational power is, okay, let's look at this 8 and this 3, which it can often be easily confused as an 8 in a linear model. Well, if you just look at where they get illuminated, because this is sort of a blurred edge detection, so it looks at multiple pixels at once and see if, and so each of this is a subsample of this one, even though it's the same size. And basically what happens is that it looks at multiple pixels at once and it gives this intensity, therefore it has a more global, or it looks at a larger neighborhood of pixels before it makes a prediction. And it also measures sort of the curvature of the angle. So you can say something like, well, I want this to be a closed curve. What does that mean? That means a few pixels of this subsampled image needs to be white at this location. And that's something that you can easily see is true here and is not true here. That's something that's easier for a linear model to pick up if this is your feature representation. Okay, that's fine. Feature engineering is extremely tedious. Some of you probably had a lot of not fun doing it for the Kaggle competition. And in part because we just don't know which features are good, right? You could like engineer and create all sorts of features, and maybe they're good, maybe they're not, and then you have somehow may come up with new ones if the ones you came up with don't work that well. So the question that deep learning addresses, one of the big motivations of deep learning is, can we just learn these features automatically? Can we learn a representation of the data automatically such that a linear model can do one? And actually, for this example we did, I actually did not handcraft these features. These are the features that are learned by convolutional neural net, which I'll describe later in this lecture. So in fact, these were features that were learned by convolutional neural net. And that logistic regression model was a convolutional neural net that achieved 90% accuracy, a very simple one. The more complicated ones can get almost perfect accuracy on the phone. Okay, so the outline for today. Introduction to deep learning, so what is the sort of the basic idea? Then a deep dive into a specific type of deep learning models called convolutional networks, which is probably the most visible form of deep learning today, certainly the one that really put it on the map initially in the last 5 to 10 years. Go over some tips for training deep networks and a brief overview of a few other fundamental deep networks that people have looked at as well. Okay. Okay, so recap. A one-layer neural network looks like this. I'm using I'm using this type of representation. It's mathematically equivalent to many other representations. So each feature with x is one of these sort of circles. So this is a three-dimensional feature raw feature input. So it takes an x, it weights. So each of these edges has a weight. So this is your w, sums up the w, right? And then maybe there's a bias term here as well. Applies a transfer function, such as a sigmoid function. That's what tau is, and then that gives you your output. And this is what's called a neuron in artificial neural network language. Right, so this tau function can be like this, just one of many choices. And of course, this is equivalent mathematically to logistic regression. Right, logistic regression is exactly this with a sigmoid transfer function. And you can train this using gradient descent. So this is a one-layer neural network, mathematically equivalent to logistic regression. A two-layer neural network basically says, okay, well, let's have two layers of neurons. Each individual neuron is equivalent in isolation to logistic regression. So let's have a layer of these neurons here, and then have the output of these layers of neurons be the inputs to another neuron at a top layer. Right? And this is called a hidden layer in deep neural network lingo. Right? So the first layer takes as input the raw features, and then outputs something, right? And then the second layer is just a single neuron that takes as input the outputs of the first layer and then outputs the final output. So this is a nonlinear function because it's a summation. It's a combination of our nonlinear transformations of the data, of the raw data. So this is not a linear function. And so it turns out that this type of network, even a two-layer network, can approximate arbitrary functions, right? Because of this nonlinearity. Provided that the hidden layer is larger. Certainly you need more than two neurons in the hidden layer to approximate very complicated nonlinear functions. This is what's called, and as the hidden layer grows in size, this becomes what's known as a fat two-layer network. A deep neural network, what's commonly called deep, is one that's simply many, many layers, right? The number of hidden layers is much more than one, right? So the first sort of truly popular deep neural networks had maybe 5 or 6 hidden layers, right? So that's sort of a lot more than one. And so basically it looks something like this, right? You have your input layer of raw features, such as pixel intensities. You feed it into a hidden layer of neurons, each of which in isolation is logistic regression. The output of this is fed into another hidden layer of neurons, each of which in isolation is linear logistic regression, so on and so forth until you have an output layer. And at each level in this hierarchy, the hidden layer is learning a function that's a combination of nonlinear transformations of the previous layer, which is a nonlinear transformation of the previous layer before that. So why would we prefer a deep network over a wider two-layer network? And anyone have any guesses?
What's the difference between neurons? It seems like they're all connected the same way.
Their weights are different.
Okay.
Yeah, so like this one might activate for certain features, this one might activate for certain combinations of features. Yeah?
Do you need more, so I guess if you have only 2 layers, then you need a lot of additional neurons, whereas if you stack them, you need less neurons. Is that expressiveness?
That's right, so that's the right answer. So deep network is a more compact model. In order to model this network using a two-layer network, you would, in the worst case, need an exponentially large two-layer network. And this has close connections to the expressive power of circuits. How many of you have taken sort of theory, computation, circuits, stuff like that? A few people. Okay, so in one of the sort of ways to model complexity of computation is using circuits like AND and OR gates, right? So if you have some raw inputs, so let's say they're binary booleans, and the output is OR, a bunch of ANDs and ORs of the raw inputs, then we could ask the thought experiment: how many gates is required if we only had depth 2, right? So imagine a multi. So here you have to imagine there's a multi-way AND and OR gate. You could take multiple ANDs and ORs. But yeah, if you only had 2 layers instead of 4, right? How many gate circuits do you need to model this? And the answer is exponential, right? And one can also show this analysis for deep neural networks. Here's just one of the most recent papers on this topic. that does the similar type of analysis for deep neural networks. And deep neural networks actually, in some sense, share a lot of commonalities with these Boolean circuits, right? So, for example, this transfer function, these functions, right? You don't have to just sum. You can actually inject a min and a max, right, inside these networks, right? And a min, if f is real value typically in a neural network, but if f is just Boolean, like between 0 and 1, then n is equal to min and or is equal to max. And this actually comes into play in the convolutional networks that I'll talk about later in lecture, where we actually use the max for the or in practice, right? So there is actually a very sort of tight connection between circuits and deep neural networks. Yeah.
So in particular, you replace the sigma first and the or, right?
You actually do both. You do sigma and then you do and then you don't replace. You just add the and get in there. Yeah. It'll become clear in the middle of the lecture. But sort of just as a conceptual thing, just if f were guaranteed to be Boolean, discrete Booleans, then these equivalences are equivalent, right? Just that now in deep networks, everything's sort of smooth and differentiable. Or not smooth, but at least differentiable, mostly. Okay, it'll become clear. So what happens, here's another thought experiment. What happens if we don't have a transfer function, right? So the output of this guy is the summation of the raw features with some weights. The output of this guy is the summation of the raw features with some weights. And the final output is the summation of the two hidden layers, the outputs. Can anyone tell me if we just use linear, if it's just purely linear, what happens to this network? Yeah.
It's basically the same as a linear model, right?
That's right. So if you don't have a nonlinear transformation as the output of the hidden layers, it collapses just to a single. The whole deep network would just collapse to just a linear function, right? Because everything's a linear combination of the raw features. Right? So the nonlinear transform that you apply to the output of every hidden neuron is essential to achieving sort of arbitrary function approximations, introducing nonlinearities. Yeah.
Do I understand correctly that if we wanted to model a deep network or a bad network, then the VC dimension modifier and will lead to overfitting, or?
So people are interested in this question. This is a question that is of interest in the community. The intuition is yes. There is not a really satisfactory formal analysis, I guess, but the intuition is yes. The belief is yes. The belief is that these super fat, shallow networks are much more susceptible to overfitting than the deep networks. Yeah. But again, there is no satisfactory formal proof, in my opinion, of this formal analysis of this. Okay, so how do we train neural networks? In the supervised case, which is what we'll focus on in this lecture, we just do so via graded descent. We have some label, right? Some training set of labels, and we have the raw input features, and we just do graded descent, right? And so you've seen this slide before, but the basic idea is that if you want to take the gradient with respect to W2, which is the weights, which is the vector of weights of this guy and this guy, of some loss function, then you just apply chain rule. I don't want to work any. This is pretty self-explanatory. You just have to work out the chain rule. You have a loss function like log loss. You have this is all differentiable. This is differentiable. You just apply chain rule, and you can do that for computing the gradients of this guy or of any of these weights. You can apply using chain rule as well.
So if the gradients, is this convex or?
No, it's
so
not.
You wouldn't expect this to be very useful then, right? You don't have complexity. Because you can drop the local minimum left and right.
So certainly it is not. You don't. Okay, so let me. There's several layers of your question. No pun intended. So it is not necessarily the case that a convex problem gives you a useful answer, right?
Okay.
It is the case that if you can formulate a useful problem as a convex optimization problem, you're guaranteed to get a good answer.
Right.
But that presupposes that the convex formulation is useful, right? It is not the case that if you have a highly non-convex problem, that a local optima is less useful than the solution of a convex problem that is not as good of a model.
Okay.
That was a slightly convoluted
Fair enough, I see what you're saying.
semantics, right? So none of these things are guaranteed, right? There's assumptions and caveats prepended to each of those statements. So
I'm
we
saying
shall.
that it's very likely that we get stuck in a local optimum. here.
That is, you're definitely going to get stuck in a local optimum.
Okay, okay.
The question is that better than a global optimum of a linear model? And I think you'll see by the end, understand by the end of this lecture why the answer often is yes. Not always, but often. There are ways to, and maybe people who are more mathematically inclined will find these things hacky, but there are ways people have built up over the years to initialize the models and set them up in a way that in local optimum they converge to tend to be very good. So people from sort of the computational neuroscience community call this backpropagation. Turns out it's just equivalent to gradient descent with chain rules. But you might hear people refer to this as backpropagation. So obviously, by calling them deep neural networks, there must be some biological inspiration, and indeed there is. So David Hubel and Torsten Wiesel discovered that there are simple cells and complex cells back in 1959. The way they did that was they put a bunch of sensors of electrodes recording the neural activity of a cat as it watched various stimulus, right? And so some cells in the brain of the cat activated for simple patterns, like a line at certain angles, and other cells activated for more complex patterns, right? Like a shape of a certain kind, or certain types of behavior, like spiraling and stuff like that. So if you're interested in details, you could, actually that's just image source, but you could read about it on Wikipedia. So what that means is that the hypothesis here was from this observation, was that it appears that these cells seem to take as input the activations of the simple, quote-unquote, simple cells in order to create their activations, right? So this is an observation made in 1959. And indeed, we know now, at least at our course level, that the brain indeed is hierarchical. So in particular, the one that has gained a lot of attention recently is the visual cortex, right? We know that the visual cortex is hierarchical. There's things known as V1, V2, V3, which are regions of the visual cortex. And V1 is known for processing edges, V2 for basic shapes and things like that. I'm sure there are computational neuroscience people here who know a lot more than I do, so I'll just leave it at that. But we know that the brain is hierarchical. And so there are different areas of the brain process lower level semantics versus higher level semantics. Of course, it's great that we have a biological inspiration, and many things, great things do come from that. But from an engineering standpoint, let's not get too carried away from taking inspiration from biology. I don't believe there is a single mechanical, artificial flying machine that flaps its wings, right? And do we even need wings per se, right? Like this, you can make an argument that this thing doesn't even have quote-unquote wings, right? And the truth of the matter is that for the most part, there are some very important exceptions, of course. And these exceptions are very, very useful. But for the most part, I would say that these days, a lot of the work in deep learning is not biologically inspired. Right? The original inspirations created feed-forward networks. The field is now called deep learning rather than deep neural networks, right? So this is a more common way to refer to these, this field. And in a sense, we could just think of this as automated feature learning. Now, of course, many people in neuroscience think about interpreting the brain as sort of layers and layers of distributed representations, and that's also what we're doing here, right? But there is no sort of direct biological inspiration in many cases. And so what that means is we want to introduce certain types of biases into the model that, or architecture, if you will, that's what they call it, that makes it more likely that the network learns certain things, and then introduce optimization tricks so that the network converges to a good local optimum. And we'll see one example of this in terms of convolutional neural networks, which is biologically inspired, actually. Okay, so any questions on generic deep learning? Okay, so convolutional neural networks. So before we talk about convolution networks, let's talk about what a convolution is. So a convolution is simply a sliding window to run an image. In this case, it doesn't have to be an image in general, it's signal processing, but in our case, it's going to be an image. And the intuition is that images typically have invariant patterns, right? For example, if we want to build a convolution of the text gradients, like there's an edge from top down, that can happen anywhere in the image, right? That's a property that can happen anywhere in the image. It's somehow more semantically complicated than just pixel intensities, but it could also just happen anywhere in the image, right? And so we detect these things via convolutions. So this is what a convolution looks like mathematically. So suppose we have an image patch, I'll call it X, right? So this is a subset of the image, like maybe a 3x3 or 5x5 or whatever sub-array, sub-matrix of this matrix of pixels. We're going to convert this this patch, this sub-matrix of the matrix of pixels, into a single number via convolution. And the convolution is specified by this parameter W, and it's simply just the dot product, basically, the matrix dot product of this W with this image patch, right? And this returns a single number. And so if this window, this patch in the image, has an edge from top down, and this W encodes for that, it'll shoot out a 1, saying that there's an edge gradient going top down at that patch in the image. So here's a left to right edge detection 3x3, right? So in the case of just black and white images, the edge detector basically says, I'm going to take whatever the x's are, zeros and ones, let's say, they're just black or white. And we're going to take a subpatch of that, and I'm going to take the positive of the right column, subtract it from the left column, and that gives a positive answer. That means we had a color gradient from left to right. And when we have this when we have this filter, which let's say is 3x3, it could be slightly larger, you basically just slide it across the image, right? But it goes like this after you slide across the image. So this is a convolution. Right? This is one that I created by hand. Convolution networks learn these convolutions automatically. So the most common type of convolutions that people, also known as filters, convolutional filters, used in machine vision, I don't know if they're the most common, but one of the most common are called Gabor filters. And so typically they visualize them because they're typically bigger than 3x3. You don't want to look at numbers. The numbers are hard to visualize. Typically just visualize. This is just a visualization of a matrix that looks like this. In fact, this one corresponds to this one. Maybe this is bigger than 3x3, but you see the connection, right? So these are Gabor filters. They are edge detectors, right? They detect edges of various orientations. Right? If you see a gradient, sharp gradient from one color to another, then you can do it. So you can do this not just for grayscale images, but you can do this at every channel, every RGB channel, right? Other types of filters are Gaussian blur. Like you want to know what the average color is of a bunch of this neighborhood. That's what Gaussian blurring does, right? And the Gaussian blur filter looks like this, where it sums up things closer to the center and then weights things less. It's a weighted sum of the neighborhood of pixels, right? It's a Gaussian blur filter. And you might want to do this if you don't care about, the patterns, but you just care about the average color in this neighborhood. Maybe that's the thing you really care about. So deep convolution networks, the main motivation is we want to learn layers of convolution filters, right? And each subsequent layer will apply convolution to the outputs of the previous convolutional layer. So it learns convolutions upon convolutions. And between convolutions, there's a nonlinear transform, of course. Right, so the convolutions are linear operators. So you apply nonlinear transform. Otherwise, all the layers collapse into a single layer of convolutions again.
Quick question on the previous slide. So when you apply a convolution layer like this, are you changing the dimensionality of the image?
That's right. So the answer is yes, and it'll become obvious sort of operationally in like 10 slides. Sorry.
So
But the answer is yes, yes. So the dimensionality of the data is equal to the number of hidden unit activations. So the dimensionality of the data is equal to the raw pixels, the layer 1.
Yeah.
After, at the input layer. After layer 1, it's equal to the number of hidden units from layer 1. At layer 2, after layer 2, it's equal to the number of hidden units at layer 2. And then when you finally do linear logistic regression, the dimensionality of the image is equal to the number of hidden units at the final hidden layer.
So in the example, for example, with the Gaussian blur on the valid image in a few slides, and that was at the bottom at, let's say, 10 pixel radius. So is the final image like 10 pixels shorter on each side, or?
It can be, there's different ways of doing it. We'll be talking about a method called max pooling, which can reduce it by an order of magnitude, like cut it in half. Like if this was 50 pixels wide, this might be 25 pixels. Yeah. But yeah, the dimension, it's certainly the case that these the output layers in the actual convolution networks that we see in practice have lower dimensionality than the raw pixels in terms of the width, size of the image. Okay. So this is a convolutional layer, right? This is a convolutional filter. This is the raw pixels, and the output is this. And then if the image is negative, so we need a nonlinear transform. So the nonlinear transform that is most popular these days for the hidden layers are called rectilinear transforms. And what is a rectilinear transform? Well, it's simply you take this image, which has both positive and negative values, because this is a negative and a positive, and we just clamp it at 0, right? Then it looks something like this. So this is the main unit of operation of a convolutional neural network. You have a set of convolutions. You have a nonlinear transform called the rectilinear transform, which just clamps it at 0 if it's negative, and then we output this to the next layer of neurons. The other thing that we do, which is called max pooling. So this is again something that is biologically inspired. The basic idea is that let's assume that we've learned a convolutional filter, and this convolutional filter corresponds to an eye detector. How do we make this filter robust to the exact location of an eye in the image, right? Like for different images of human faces, the eye could be a little bit to the left, a little bit to the right. It doesn't really make a difference. But the output of the convolutional layer would have the activation either a little bit to the left or a little bit to the right. So how do we make this less jittery of an output, right? And the way we do that is a method called max pooling, which basically is we take the output that we actually send to the next hidden layer is the maximum response of, say, a 3x3 window of outputs. And this is mathematically equivalent to an OR gate if these outputs are binary, but they're continuous in this case.
So there's something I didn't quite catch. So in the previous slide, you said we use max. And then you said we can use the chain rule super easy. But won't we get non-continuous gradients?
It's only non-continuous at a single point.
Okay.
Which happens, if I want to be sort of annoying, it happens with measure 0 over a set of measure 0. Right?
Okay. Okay.
It's discontinuous. It's continuous almost. It's differentiable almost everywhere.